Hey guys, in this video I'm going to be showing you how to calculate the angular velocity of this rod when it reaches the vertical position. So basically we're finding out what the angular velocity of our rod is when it's in this position just here, assuming that the thing has been released from rest. Okay, now I've done this problem a few times before using energy methods, but in this particular video I'm going to be showing you how to do it using Newton's laws, namely the sum of forces is equal to ma, and also the sum of torques acting around a point is equal to the moment of inertia around that point times by the angular acceleration. Now in order to progress with this problem, we need to draw a free body diagram of what our object looks like sometime mid-flight. So let's do that. This is what our object looks like sometime mid-flight just here. Bam. In fact, let me get rid of these pin supports just here. So we've got a pin just here, and we know that there's going to be a force due to gravity just here downwards, always downwards, of mg, and we're also going to have reaction forces due to the pin. And I'm going to choose, for the sake of simplicity, to draw our x to be in this direction just here, and our y to be in this direction just here, purely for the sake of simplicity. And you might see why in future problems. It probably won't come in this particular problem, but it's usually good convention to write your forces like this. Anyway, now because this is an arbitrary position, I need to actually describe its position relative to, say, the horizontal or the vertical position. So I'm going to choose to create a new variable here, which I will call theta, which describes the angular displacement of the bar from its horizontal position. I could have chosen theta to be from the vertical up or from the horizontal down. I could have chosen whatever I liked, but I think it'll be convenient to use this value just here. Okay, so now we've got our free body diagram sorted. Let's actually apply these two formulas just here. Well, I'm going to choose to take the sum of torques around point O. And let me clarify what I mean by point O. This right here, this pin support is point O, and this point right here, the center of mass, I call point G. Okay, so I'm going to choose the sum of torques around point O is equal to IO alpha. Okay, so in order to do this, you might be thinking why I got the sum of torques around point O. That's because I neglect these forces just here. Anyway, I won't jump the gun. What's the torque due to this force mg just here? Well, we need to split it into both its horizontal and vertical components. So let's do that to the side. This is mg just here. Drawing it slightly larger. This is mg. This is its component in the y direction. This is its component in the x direction just here. And we know that this angle right here, this angle here is theta just there. Which means we know this angle here is 90 minus theta. Which means we know that this angle, because it completes the triangle, is equal to theta. Let me clear the other stuff out. And bam, we're left with this. That's just a little bit of trigonometry revision just there. So let me clear that out of the way as well. So that means that the component of mg in the x direction is mg sine theta, and the component in the normal direction, in the y direction, is mg cosine theta. I should mention that I've clearly defined this to be positive x, and I've defined this to be positive y. Positive y just here. Okay, so now that we've split mg into its two components, now we can take the sum of torques. Notice that the component of mg acting in the direction of the rod will not produce a torque. That's because if I were to redraw this mg, it will actually look like this. It will have a component in this direction, and it will have a component in this direction just here. Right? And the only component that will produce a torque is going to be mg cosine theta just here. So let's do that. This will be, the sum of torques will actually be mg cosine theta times by the distance from the axis of rotation towards your force, which is L on 2. So that's times by L on 2, and that's going to be the moment of inertia around point O times by the angular acceleration. Notice the torques due to Rx and Ry are 0. That's one of the main reasons I chose the sum of torques around O. Okay, so let's solve this now. Well, we know this is going to be, in fact, let me draw it all in white from here on in. That's mg cosine theta times by L on 2 is equal to I-O. What's the moment of inertia of our bar rotating around its end point? Well, we know that, in fact, let me draw it here. We know that the moment of inertia of a bar rotating around its center of mass is equal to I center of mass is equal to Ig in this case, is actually equal to 1/12 ml squared. Right? And we know using parallel axis theorem that if we were interested in finding the moment of inertia around point O, which we are, that means I-O is actually going to be equal to, using the parallel axis theorem, 1/12 ml squared plus m times by our distance, which is L on 2, squared. Just to reiterate, that's using the parallel axis theorem, which states that the moment of inertia around any point is equal to the moment of inertia around the center of mass plus md squared, where d is the distance between your new axis and your center of mass axis. Okay, that's from a previous video, though. If you don't understand that, I totally recommend you look at my previous videos. So let's fill this in. We know I0 now is just going to be equal to 1/3 ml squared. So let's fill that in. That's 1/3 ml squared times by alpha. Okay, let's get a little bit more space in here. So let's push that off to the right. And we're left with mgl cosine theta on 2 is equal to 1/3 ml squared alpha. Alright, so we're going to get back to this equation in a second. We need this equation to solve the problem. But first, let's take a minor detour. What is our angular acceleration anyway? Well, we know it's our change in rate of our angular velocity with respect to time, d omega dt. But you could also write this using the chain rule as d omega d theta times by d theta dt, just here. Right? So what we can actually do is we can rewrite this out as d omega d theta times by d theta dt, which is actually omega itself. That's really quite an interesting result. And so what you can do, and remember this is just alpha just here, what you can do is you can actually group this together. You could say this is, actually let me do it in one step, this is alpha d theta times by omega d omega. Right? This is a very bizarre result to expect, but it's really quite an important one, because what we can do is we can actually sub alpha from this value into this value just here. So if you get everything in this equation in terms of alpha, you'll find it'll be 3 mgl cosine theta over 2 ml squared times by d theta is equal to omega d omega. Okay, and once you solve for that, noticing a lot of these terms cancel off, you're left with 3g on 2l times by the integral of cosine theta d theta is equal to the integral of omega d omega. This is a very bizarre concept. I can appreciate that, but just bear with it. I think you might actually get this as I progress through it. Well, we're going to be integrating based off our boundary conditions, which are going to be, in this particular case, the fact that theta is going to be equal to 0 when omega 1 is going to be equal to 0. I hope that makes sense. Basically, omega 1 is going to be equal to 0 because this thing is released from rest. And that's when theta is equal to 0 based off our definition of theta. So if we can plug that in, we can plug in our first two boundary conditions. First of all, theta is equal to 0, and omega 1 is going to be equal to 0. At omega 2, we know that theta is going to be equal to 90 degrees. And let's have a look at this just to be sure. When theta is equal to 90 degrees, this entire rod will be vertical. So let's draw that in really quick. This is going to be 90 degrees, or if you like, pi on 2 radians. So let's actually substitute that in. We're left with 3g on 2l times by the integral of cosine theta, which is actually just sine theta, and with limits of pi on 2 to 0. And let's do the right-hand side. What's omega integrated? It's just going to be omega squared on 2 with limits from omega 2 and 0. So once you plug through the mathematics, what we're left with is 3g on 2l, 3g on 2l, times by sine pi on 2, which is just 1, minus sine 0, which is 0. And on this side, you're left with omega 2 squared on 2 minus 0. And solving the algebra, you're left with 3g on 2l is equal to omega 2 squared on 2, leaving you with the final solution. I'll draw it up here. Omega 2 squared is going to be equal to 3g on 2l once the 2's cancel off. Sorry, it's going to be, once the 2's cancel off, so it's going to be 3g on l. And you're left with omega 2 is going to be equal to the square root of 3g on l. Alright, that was a much harder type of way to solve this problem. It had nothing to do with energy methods, but you still get the right answer after all. So this really demonstrates that you can actually solve any particular problem any way you like, as long as you apply the formulas correctly. As a brief aside, I could have done the sum of torques around point G as well to solve this problem, and you'll get the same answer, but it involves simultaneous equations, which are a little bit longer. Nonetheless, I hope that makes sense, guys, and I really hope you learn a lot from these three different methods.